Hello everyone, my name is Dr. Sharidya Rahman, so one of the research fellows at Monash University in Melbourne. So today we'll be talking about freestanding or suspended 2D materials and many more interactions that can result in 2D materials from them being suspended or being freestanding. Let's start by looking at some background and motivation. So when we say about free body particles or many body interaction, they often result when it comes to the reduction of dielectric spinning. The dielectric, so one of the major sources of dielectric spinning is a substrate. So as we know, in a particular 2D method, there's a Coulombic interaction between the positive and the negative charges. And when we have a substrate, it actually causes a variation in the attraction in the Coulombic force pattern. And as a result, this influences the Coulombic interaction. And whenever there is a substrate, the Coulombic interaction tends to decrease. So whenever we don't have any Coulombic interaction, this Coulombic attraction or interactive forces is very strong, and as a result, it can lead to the formation of many body particles or many different kinds of fancy particles at room temperature and low temperature. For instance, one of the work over here has demonstrated many body particles at room temperature and at low temperature. For instance, in this particular work, the authors have exfoliated two-layer molybdenum diacrylonide, and they were able to suspend this 2D material on trench for dielectric on trench substrates. So these trenches can be created by using etching or dry etching or wet etching. And eventually those 2D material could be transferred by mechanical exfoliation and then when there was transfer technique. So due to the trenches, they were able to reduce the dielectric spinning, and as a result, they were able to emit biexcitons and ions at low temperature. So this is a curve showing the black one is showing the curve on silicon dioxide, and then the red one is the one that is freestanding. So we can see from the freestanding one, there is an emission of acetone ions, and eventually there is a biexciton emitting a bit low energy at 6 Kelvin. So this emission of biexcitons is actually taking place because of the reduction in the dielectric spinning. And this results in the formation of many body particles, which have a lot of several applications in optoelectronic devices. So eventually in this particular work, the authors were able to obtain these biexcitons of many body particles at room temperature. So they did the engineering 3 parameters. So one is, of course, the dielectric spinning, which is basically coming from the reduction in the dielectric, the reduction of the substrate interference. And the other two is the excitation power and the density of the trions. So by modulating the excitation power, they were able to modulate the density of the trions. So using a high power, they were able to obtain biexcitons at room temperature, which is basically has very good applications in single photon emitters and of course optoelectronic devices. This particular work was a very good motivation very good motivation for many body interactions with many body particles, including materials. So this kind of suspended 2D materials have been demonstrated eventually in multiple work. So for instance, in this work, the people have demonstrated monolayer WSE2 on a thin substrate. So they were able to fabricate monolayer WSE2 on multiple trenches. So these trenches, they can help to reduce the dielectric spinning. And as a result, they were able to enhance the quantum yield or the quantum yield of the photoluminescence yield at room temperature. So as you can see, the red one is the one on the supported area, and the blue one is on the suspended area. The suspended area, as you can see, the quantum yield has enhanced with thousands and thousands of times. This particular property is very popular or very important when it comes to applications in photovoltaics, LEDs, and the photodetectors and many other electronic devices. So this quenching, this enhancement of the photoluminescence yield can also take place in 2 layers and even up to 3 layers. So in 2 layers, they were able to enhance the quantity like both excitons and trions, and even up to 3 layers, they were able to emit many body particles in multiple layers due to the reduction of the dielectric spinning. So eventually, the researchers have also shown that second harmonic generation can also be elevated by enhancing the second harmonic by reducing the dielectric spinning, and of course by reducing dielectric spinning by reducing the substrate interference. So of course, the researchers have also actually tried to create many different kinds of trenches. So as we talked about, this is a circular trench with a particular diameter and a particular hole depth. This is a very common design of a trench. However, eventually researchers have designed many different kinds of trenches. For instance, they were able to design this kind of Chinese zodiac signs, and they were able to show that based on the lining or based on the structure of the trenches, the luminescence yield can take the shape of the particular trench. As you can see, this particular as you can see, one of the 2D metrics being transferred on the overall area has only higher photoluminescence yield only on the areas that have reduction in the dielectric strain. As a result, as you can see that we have very high photoluminescence coming only from the trench area, and it is taking the shape of the particular trench. So which is very interesting and I think they also have very good application in photovoltaics. So as furthermore, people have also shown that this kind of suspended 2D materials, the suspended material actually have very good electron mobility and is also very good application in transistors and field effect transistors. For instance, suspended graphene has actually a very good, very high electron mobility and has a very high electron mobility. And this has been demonstrated several years back already. So these are the few applications that we have on suspended 2D materials. So let's look at a few examples. For instance, we have something called a pressure sensor. So as a result, as we can see in this particular work, authors have fabricated this kind of metal bars using electron beam lithography, and they were able to transfer this particular 2D material and so forth. And based on the pressure being applied on the interfaces, they were able to convert this pressure to a voltage, and which is eventually work as a pressure sensor. So similar work has also been done in this kind of cavity as a content channel. This can also work as a kind of a resonance. And we're able to measure the resonance frequency, including the pressure at which the resonance frequency is occurring. So this kind of suspended 2D materials have also been applied in many different kinds of sensors, which actually forms the integral part of many different devices. So finally, 2D materials have also been, this kind of suspended 2D materials have been applied in ultrasound detectors and also accelerometer. In ultrasound detectors, graphene had been used as a model 2D material, and they were able to design this kind of systems as in the form of suspension, and which can be eventually converted to an ultrasound detector. So also in this kind of work, and they have been using accelerometer, and this is the particular work, and this is the particular response rate at this particular frequency. Taking some motivation from this previous work, so recently we have published a paper where we have suspended the tungsten disulfide and tungsten heterostructure and onto a cavity. So the cavity is basically a trench substrate, and as a due to the trenching, we were able to we were able to reduce the dielectric spinning. And as a result, we were able to increase the quantum yield, and then we were able to obtain many body particles at room temperature, including multiple excitons. So this particular work was recently published. I've taken motivation from many different works that have been published in the past. Thank you everyone for listening. So this is all.